sorry for the technical glitch, and I need to start with the so that so basically hit the course start date and we so the other things so the way to say and value of fluency in velocity and know the equation uh, here so the integration like now yeah the way equation is like this and the equation is from the equation also the electron for this equation and the field and the like solution observation flows this is like function the function has to be like x and v it is in 1D and it is second twice differentiable the in the second condition. So for the cosine like for the solution of this equation uh, we like in school and I will be called and for this cosine sine like summation is to the appropriate b and constant b and c we get for a cos exponential means that is a case but this total thing is this because like is actually initially total face just e minus yes and with respect to this we take the so here here we have plot the value for the so much on the medium respect to the difference in between could be this and the differences specifically x axis change so cannot time period then it is time time axis is called time period and the phase can be written as k so it the first part of the first week of the class discussed and in the first week I have also discussed a problem going to this so yes the how there will be conversations and so we consider in charge and library. Yes, did that. Many and as in the United States and so they are all satisfying the thing of with if you could and you could have I so also you need to remember also form of so form of how so copy is and what is what basically also having things and how the real web actually is the real web actually playing with or not because playing with has infinite energy and power which doesn't exist basically. Like, exist. So people with me because we have to find nature. Physically from this way. more sophisticated beyond the solution of the document is which K dot. So why we like to like cause theta as a participation function by we part and take full expansion. Those things have been discussed in the classes. So we also will discuss with the field and all those things. Uh, Another important thing like mathematical calculation is here. There are a question about it is with 3. So if there is two kind of a situation where is different is in polarization. Polarization is different. When the assembly elections so it's like different and the interference done. So for different polarization, basically I was Ix plus I. But for same polarization total I was I1 plus CF shell and real part of E1 dot into star plus I2. This part term was interference variance term. So like maybe second or third class, I have yes, like C. The electromagnetic waves of two field was given. So one field is traveling along x-axis and the y-axis, and how we'll get the interference I have shown in class 2. And here both are in the same polarization. So how we'll calculate that? This is the like solution. And what is I is basically so how we calculate Ix and Iy that are also have discussed. Okay. Then we we need some like concept interference. So we already know Newton's rings. When we place two pieces of glass together, then we get interesting, colorful ring patterns. And I have discussed in second class some Newton ring problems, and they are not important for exam purpose of this course, but you can like the whole purpose of discussing those things was to get a like idea how Newton's rings were formed. So they are not example only. They are not like important as as part of this course, but you should know in general. So for this course, the important is the Fabry parameter. Or it color. So you need to really understand what happened here. So here basically it is multiple beam interference, and maybe in third class I have discussed clearly that, see, so basically this is how multiple beam interference works. Like you like one beam incident on the this slab, and it get as parallel reflected waves and parallel reflected waves and parallel transmitted waves, not actually parallel. Most of the cases they are parallel, and then you use a lens and you will get a point, and that is true for also transmitted waves. And how we calculate like the things like the what will be the transmittance, uh, we also see in those on of classes. So this is the transmittance after multiple interference, and this is the reflectance. So here we got a term which is F. So F was basically 4R into 1 minus R whole square, and R was R square. So here we get 1 plus F sine square delta by 2. And transmittance are that was transmittance, and reflectance was generally F sine square delta by 2 by 1 plus F sine square delta by 2 is reflectance. And what we were generally interested was this graph, that what should be the transmittance. It was transmittance. This axis is here transmittance, and exact opposite is reflectance. And we can see that at delta by 2 is equal to m pi, we will get a maxima which is 1. When r is for this, we can see r square is 0.46, that is actually 4.6%, this is 18%. And when r is about 87%, that reflectance of each side is about 87%, we get very sharp peak, and here also very sharp declines. So why it is very important? Because to generate attosecond pulse or very ultra femtosecond pulse, we need a laser, and these etalons work as a laser cavity. So these are very important concept. Mm. So, and the T depends on thickness, angle, and wavelength basically. And from here, we also get modes, and at which frequencies we will get modes. That was like characters is by Q into C by 2L. At these frequencies, we get maximum transmission. Then we got to know that uh, this like maxima does not always attain one. They like follow some bell-shaped curve. And why was that? That reason is also discussed in the classes. Okay. This thing is called FWHM, and why FWHM? That is like for this is the FWHM. It is also a FWHM. And then the most like important concept was like and we'll get this kind of curve here. So basically we call this G omega, and this envelope was F omega, and it was in frequency domain because here it is omega. And when we get in time domain, so the curve was the same, like there should be an envelope, but these curves were f of t and these were g of t basically. So the electric field in time domain was basically this function into g of t f of t, and electric field and frequency domain was this was step function or repetitive function g into omega into f of omega. So I know I should have used two different colors. So here you see the basic thing is that f omega is a envelope. So its width is very high, but when we always know that delta omega and delta t is a constant. So if delta omega is very large, delta t is very narrow. So when we do the Fourier transform or inverse Fourier transform, we see that this envelope made this like spikes, and the spike here made the envelope in time domain. Then we need to remember the important concept, it's free spectral range. So there was lambda FSR, which was free spectral range, which was lambda square by L. L is the like thickness of the etalon. And remember here, this is multiplication, that is convolution. This signature is basically convolution. Then come a concept which is line width. So line width is basically FWHN of transmittance peak. So what I was telling that this is actually FWHN full width at half maximum. Maximum is 1 and this is 0.5. Okay. So for this portion, this is like FWHN very up of that. So the line is basically, we can say the line width was, and the W is lambda square by L y minus R by into R. And how it came to this formula, that is also discussed. And then another term comes, which is finesse of interferometer. That was free spectral range by FWHN. And by that line width. And that comes to root R1 minus R into pi. And for best reflectors, for 99.99%, basically, root R is almost equal to 1. Then this coefficient of pi fineness will become pi by 1 minus r. So basically, finesse is the number of is the number of wavelengths interferometer can resolve. It is the quality factor of resonator, and it is also shows the resolving power uh, of the resonator. And we need to remember the what is the new FSR. So that is C by L. FSR basically distance between two peaks. Then briefly the professor has discussed some optical cavities. Cavities and their like stability point, stability condition. And there was one question about this in like quiz. So basically, how those like for stability point of view, we need to calculate like G1, G2 needs to be greater than 0 and less than 1. That is the stability criteria. And G1 or G2 can be calculated as 1 minus L by R 1 or 2. So then there we will get a plot like this, and the point like this condition in a graph is denoted by kind of this. So the point should be inside this shaded region, the like G1, G2 point. So this is G1 axis, this is G2 axis, and like the laser point should inside this shaded region. So for optical cavities, only this portion is enough. And like if you want to like go through more about this, there is a course of lasers in NPTEL. You can go there, but for this course, it is this course initial purpose. Only this stability criteria, how it works, it is enough. And what is the G1 and G2 for different kind of laser cavity or optical cavity, like for plane parallel cavity, concentric, spherical, how they are placed, then confocal, hemispherical, concave, convex, means you need to like calculate those things. Then comes Fourier transform concept. So basically, before, okay, let's get- go through Fourier concept. So in frequency domain, this is called Fourier transform FFT, and another is called inverse Fourier transform IFT. So this is ET exponential minus I omega t dt. This is the relation how we convert from time domain to frequency domain, and this is the relation how we convert frequency domain to time domain. And what is basically the spectrum? The spectrum is in frequency domain. It's basically like this: the square of Fourier transform of f of t whole square magnitude square of Fourier transform f of t. So then we need to go through some Fourier transformation. We need to remember these things. Properties like scale function. How does scaling work? How does that work? Some properties of that shift. How do that work? Complex conjugate. That was like F star T derivative is that's T modulation. So this hints how, so if we know f of t, the Fourier transform of f of t, then we should know the Fourier transform of ft by t, ft plus dt, then ft minus tau, f star t, f dash t, and the modulation of t. Basically, so we get to see that Fourier transform of f of t by capital T is basically like this: omega t. And for complex conjugate, basically it is the, if the function is real, that is like we are considering light wave, F star t is equal to t. So Fourier transform of f star t is basically Fourier transform of f of t. So the good part, a good trick to remember this, like if time period, like peak gets narrower in time domain, it gets wider in frequency domain. So that is the reason here you multiply with t. And for the derivative, it is like I omega equal omega. And for shift, we get exponential minus I omega tau f of. So when we are transform of f t is f of omega. So I have discussed all these things in detail in fourth class, you can see. So I have also mentioned that in different book and or different literature, this 2 pi factor has been incorporated in different ways. Like in some book like H. Katas, instead of 1 by 2 pi, we get to see 1 by root 2 pi in both the equation. Okay. So these are the thing. And we have also, I have also shown the scaling property, like the shifting property. You can see that for plus we get minus, and for minus we uh, get plus here. The modulation theorem, like if we are modulated by cos term, then that would be half of Fourier transform t minus a plus half of Fourier transform t plus a. And this is how it modulated. Then we get another theorem, which is Parseval's theorem, that says that if a function is ft and another function is gt, then integral minus infinity to plus infinity ftg start t dt is equal to integral from minus infinity to plus infinity f omega t omega. And here I have written some important like output of like integration, that is 0 to infinity sine a omega by omega d omega should be pi by 2, and 0 to infinity to the power minus omega square d omega should be pi by 2. And when there is e to the power minus a omega with sine b omega d omega, we get b by a square plus b square. When it is cos b omega d omega, then it is a by a square plus b square. And if here we get a constant term with omega square, that get us root over pi by 8. So, and this is the most important thing, exponentially to the power minus a omega square plus b omega d omega. That gives us pi by 8 e to the power b square by 4a. So, these are very important, like this thing, e to the power minus a omega square plus b omega d omega root over y by 10 into the power b square by 4a. So this is actually a very important, like direct solution. And I have discussed some examples. You should go through these examples. Like I have mentioned that you should not go through Newton's rings questions for the exams, but you should definitely go through the Fourier transform examples I have discussed, and if you can go through the another kind of examples on your own, that would be great. Always remember the Fourier transform of different functions, that like direct delta function, cosine function, then sine function, like that, step function here, or this is the Heaviside function. So these are important. And one quiz, whole quiz for week 4, week 4, or week 5, it was completely in question of the Fourier transforms. So in week 3, I have also discussed how the Fabry-Perot echelon can resolve two different wavelengths. So these are very conceptual questions. This is the reflection of coefficient. This is to calculate half finesse. That is important. That was asked in a question. But this question, that was not that important for this course. But we should know the resolving power and this kind of thing, the ratio T max and T min, and all those things. These are very important. And here in the fifth class, I have shown how you need to convert each this integration to exponential minus a omega square plus b omega form. Then you could totally get to the answer very quickly. That's the trick. And here also I have discussed some Fourier transformation from time domain to frequency domain for Gaussian shape wave, hyperbolic second wave, square wave, single-sided exponential wave, and then exponential wave. So these are also important to sharpen your Fourier transform skill. So those like like calculations, how we got there, is very important. So I have also here discussed that how can you use e to the power minus x squared dx formula. So here we see the Gaussian electric field is like e to the power minus 2 ln t by delta t whole square, and how we change it in frequency domain. So this is the calculation. So in frequency domain, we get something like this: e to the power minus 1 plus 4 delta t whole square 8 ln t ln 2. This is the sec function, and the sec function remains sec even after frequency transformation. But rectangular shape function doesn't remain rectangular shape. It's converted into the sinc function, and single-sided exponential, and so on and so forth, symmetric exponential function. This was the Fourier transformation of those things. So Fourier transform of different shape, different wave shape is very important. Not for only for this course, for overall purpose, like our Gaussian say function, rectangular function. And from the Fourier transformation, you also get to know transform limit. that we will discuss in a bit. And okay, then concepts are very important that for an ultra short laser pulse, the time field has been given as half of u divided by t exponential I omega naught t minus pi t plus its complex conjugate. This complex conjugate is used to make this field real. And omega naught t is basically carrier frequency. And phi t is actually the initial phase. We can say it is, and this is the total phase. And if we move move half and complex conjugate part, we get ET t exponential minus I by t. So this is the real field, and this is the complex field. Okay. Similarly, the Fourier transform of real field, we get half of S omega minus omega naught exponential minus I phi omega minus omega naught plus half of S minus omega minus omega exponential plus I phi omega minus omega minus omega naught. So you also need to know that these two terms are not complex conjugate of each other. Then the Fourier transform of E of t give us E omega Or you can like simplify this thing and we'll get this omega exponential minus I y omega. Okay. So basically you can see that here I can draw the drawing. So E omega corresponds to this peak, that is E omega, which is the like frequency domain transformation, frequency like domain of the complex time domain field, and we get something like this. These two are basically curly E omega. And we got to know that to define a pulse properly, we need two things: intensity and phase. So we need two information: intensity as well as phase. And it is very important, this part, because there were some questions in the quiz regarding this part, and the answers are also given in the answer sheet. And please, like the basic thing you need to remember that this field corresponding to complex field, these fields are corresponding to real field, and it is the frequency axis 1 by 10 to second axis. This is 0, and negative frequency doesn't count anything in those cases. Another thing is to know we can write ut as a function of uh, FWHN. So that is 1.38 T by tau FWH in whole square. Or we can write this as E naught exponential minus 2 L2 T by tau FWH in whole square. So tau FWHN is basically intensity cooled with half maximum. Always remember this is in this like nomenclature, this is intensity full with half maximum. And intensity full with half maxima is 1 root 1 by root 2 of like how I denote amplitude FWHM. And intensity. This is also a very important like thing to remember. I have t is V naught whole square exponential minus 4 into t by tau WH whole square. Exponential 2.76 t by tau and WH whole square. And how we can get the phase. So phase is time inverse imaginary part of Vt and real part of Vt. That is also a very good concept. Spectrum. We have seen the spectrum is basically can be written as like this also. So it can be the Fourier same thing. So it can be the electric field in frequency domains whole square, or you can Fourier transform the time domain field and make it square. So another thing now you will see if a pulse moved in time domain only phase of the pulse changes one in frequency domain. So you have seen that it is intensity. This time so then this shows the phase. Frequency domain. We get a usually with parts with the phase. This is the going to say. But if this pulse shifted here in time domain, here in frequency domain, the pulse is still at zero, but the phase became like this. So why it does that? Because of, see, you know how Fourier transform work because of this factor. And it also shows what phi dash can do. You need to know that here it is phase in spectrum, it calls spectral phase in frequency domain. Lambda spectral phase in frequency domain. Similarly, the spectrum in terms of lambda is spectrum noted to pi by c by lambda square. This is the Jacobian for these Laplace transformations. The factor, yeah, always remember that this kind of concept we're using uncertainty principle that delta t delta mu is almost equal to half. Then what is attosecond, femtosecond, picosecond, and all those things. So basically, we know that phi can be the function of, like, not only the function of omega, that can be a function of omega squared and all those things. So we need to take into account the group delay and what is group delay dispersion. So we'll get back into those things in a little bit. And this calculation, that is when when the average power and pulse repetition that is given, what should be the peak, what would be the peak power and intensity. Here you can see the energy per pulse. You need to calculate the energy per pulse. Then you need to, like, assume the peak power, or like the peak is almost a triangular thing. Then from that you will get the peak power, and you can see I have, like, from a laser which have a 500 megawatt average power and pulse repetition rate of 80, like, megahertz. You can see the intensity is 4 into 10 to the power 9 watt per meter square. And the electric field is 1.7 10 to the power 6 volt per meter. And the electric field in hydrogen atom is 3.2 into 10 to the power 10 volt per meter. So in laser, like when we discussed nonlinear optics in last day or last few weeks, we know that how much electric field strength should be there to, like, have the nonlinear effects of second order nonlinearity effect on numbers things. So the value to it. Calculation is really important. And then comes this thing, instantaneous frequency, which is basically omega naught d phi by dt. So previously I have mentioned in place that omega naught is carrier frequency. Omega naught is carrier frequency. If and only if omega naught is greater than phi by dt. And this is called instantaneous. Singular frequency. And this is, let me write it different color. Frequency is basically divide that thing by 2 pi, which is mu naught by d phi dt, and then by 2 pi. And the quantity is group delay, that is TGR. Remember, so that can be written like this. Then some concept is wrapping and unwrapping notes. Those are important. And the first blanking. Those are very important. span phi t, which is phase, is t by 1 factorial by 2 e square by 2 factorial and so on. And we can do the whole thing in a frequency domain also. So why we need frequency domain measurement, how we need frequency domain measurement, the spectrum measurement, why we need time domain measurement, and which is more easy to measure. Those things have been discussed repeatedly in the classes. So you need to like remember those concepts also. So omega minus omega naught. So here also this t minus t naught, t minus t naught whole square. Plus by 2 omega minus omega naught whole square by 2 factorial and so on and so forth. Two, which is d square by d omega square and omega naught. Then omega naught is called GDD, relatively dispersion, and its unit is basically this is basically its unit is basically femtosecond, is a femtosecond square. So discussed that see, so phi naught is zero to the phase coefficient, so phi naught t is equal to phi naught omega. Phi naught t is basically phi naught omega. There's the zero order phase or absolute phase, they are same. And order phase is basically irrelevant. Unless the pulse is few cycles. So attosecond pulse are basically a few cycle pulse. So this term is very important. In attosecond. Okay. Then phi 1 t comes will be the first order term. So it causes shift in frequency domain phi 2 t or that causes sharpen. And here you can see that after, like here, I have shown that how this sharpening changes the time width here. So where you can see the time width has been changed. So delta t out, basically after sharpening, the time width is like this. So you can see that this is the result of after sharpening. This is the delta t out and delta t in is before the sharpening. And here you can see that if delta t is very small, after sharpening it becomes 11 times or sometimes 20 times. But if delta t is considerably large, 160 frames per second, then after sharpening there like delta t remains almost same. So the takeaway lesson for this is basically to use some femtosecond pulses where the temporal broadening is very, very much less. And here you can see some like the time domain, like time domain envelope and intensity, and their frequency domain spectrum, the frequency domain field, phase. So and here in sharpening, you need to consider positive sharpening and negative sharpening as well. That is linear sharpening. So phi 2 will give us linear sharpening. Positive char, how that work. Negative char, how that work. And how in positive char, what is the relation between terms 10 years left and right, how that changes. Those are the thing. So, one example of linearly short pulse E naught exponential minus t by tau g whole square exponential I omega naught t plus beta t square. Omega instantaneous is basically omega naught plus 2 beta t. The Fourier transformation of Chart pulse that is also important. Then from phi p we get quadratic chart and that cause us satellite pulses. Phi 4 gave us symmetric trailing rings. Phi 5 gave us quantic phase. So for each pulse of each other phase, one need to remember. Field versus time, delay versus time graph, delay versus frequency. 8th, ninth class, I have discussed that how you can compensate like sharpening. So that is not mandatory in for exam purpose. view. Like compensate positive chirping or negative chirping. That is not that important. And what happened, the next important thing is what happened when amplitude modification that depends on alpha function index. Basically, now we may need to know how we can measure pulse length. Then there are three ways: effective width, width theorem, RMS, pulse width. Theorem and FWH and their pros and cons for each one. Another important thing is time, bandwidth, product, transform limited. Pulse and how this value is different for different pulse. Here you can see how it has been around the years. So got the transform limit for the Gaussian pulse is 0.441, for hyperbolic pulse is 0.315. How the when the shape of the pulse changes, this bandwidth product is also changes. So the, the one pulse is transform limited. That means there is no chart. That's the takeaway message. And how you can calculate those bandwidth product, I have also shown for Gaussian wave and Seq wave. Significance of this in TD, T, PP. Then you need to go to basically Proof, method, interaction, linear interaction, that is linear figures like linear polarization. Then comes the non-linear interactions that give us non-linear polarization. So non-linear polarization depend on Shannon multiplied through square resolution and multiplied easy cube and so on and so forth. And this give us second Harmonic generation. It gave us third Harmonic generation. And I have discussed those things in the last class. So also we need to go. So now the wave equation has also been changed because of this. The wave equation is inversely not square. N square E del T square is equal to mu naught del square P by del T square. You need to remember also what is normal dispersion. What is anomalous? Anomalous dispersion. So here d and d omega is greater than 0. Here d and d omega is less than 0. So frequency increases while dynamics decreases. Absorption depth. Another important factor in absorption depth, which is 1 by alpha. Then comes the nonlinear response, when the nonlinear response is relevant. Say centrosymmetric, and non-centrosymmetric, medial, even ordered, odd ordered, polarization. Self-phase modulation, cross-phase modulation. These things need to be like remembered. Conservation in law, in wave mixing, E field strength, so that we could get nonlinearity. A phase matching. So you need to remember that that or second order harmonic generation, n omega should be equal to refractive index of 2 omega, and that is not possible in a normal material. That is only possible when we have like birefringent medium, or there is a ordinary axis and extraordinary axis. High harmonics generation. And before that, professors had also been discussed the perturbation calculations. Please go through that thing also. And how high harmonics generation can be done with 3-step model. Module. What is the significance of high harmonics generation? The significance is that in general, harmonics are not strong, but in HHG method, higher order harmonics has significant same intensity almost. So from this high harmonic generation, last we can generate attosecond pulse. That is the last thing. So the course has started with only one wave, and now you can understand that how that course has evolved. First, the course goes from the preliminary wave characterization to multiple beam interference, and then because of this multiple beam interference, how it alone is good for optical cavities and how the transmission works. We got to know that. And then we wanted to know a few bits of Fourier transform. So from that knowledge, we know how the electric field change, like shape changes from time domains to frequency domain. Then we get to know the chirping. Now, when we have know the thing chirping and all those things, we know because of this phase thing, refractive index also changes. So refractive index changes, and also there is wave metal interaction. When electric field is very dense, not I should not use the uh, like word dense. The when electric field is very intense, we go to the nonlinear effect. And when nonlinear effect takes into account, there is an alpha part and then the refractive index part. The alpha part is also there. The refractive index is not anymore a real quantity. It becomes a complex quantity. And we get second harmonic generation, third harmonic generation, and so on and so forth. And from that, we move to high harmonic generation. And from high harmonic generation, we get to the point where we can generate attosecond pulse. This was the whole course. So in between course, one extra thing I have discussed, actually two, that is Newton's rings and how we can compensate charge. Those two things are not important. They are not important for fast exam. So that's for today and for the course. And all the best for the exam. Thank you.